Welcome back. This is part 2 of the angles and radians lesson. We got that 2 up there. We're going to jump right into doing this example of radians, which are the ratio of the arc length to the radius of an angle. So here I'll do a 45-degree angle. 45-degree angle is 1/8 of a circle. So, if I want to find this arc length, I need to get the arc length for the full circle, which would be called the circumference, and then I just need to divide that by 8. 1/8 of the entire circumference should give me this arc length. So the circumference is 2 pi r. Oh, I need the radius, don't I? Let's say that the radius of this one is 6 feet. 6 meters. We'll go, like we just talked about how much better meters are, so we'll go with meters. So we'll say the radius is 6 meters. If the radius is 6 meters, that means the circumference is 12 pi meters. Because it's just 2 pi times that 6. Look at this, 12 pi meters. So 1/8 of that, 12 pi meters, should give us 12 over 8 is 3/2. 3 pi over 2 meters. And I'm going to, throughout all of this entire chapter, pi is going to come up a lot. And every time pi comes up, some of you might be tempted to like switch it out for 3.14 and then actually do this calculation to get a decimal. Don't ever do that for this class. If you're doing an engineering project and you really need to know like how many inches something is, definitely do that. Get your approximation. For pre-calculus, we want to make things be as exact as possible at all times. 3.14 is not exact. That's an approximation. So we're never going to use 3.14. We're always just going to use the symbol pi. And we can just leave this as 3/2 pi. That's exact. It's nice. We'll stick with that. So 3/2 pi meters is the arc length. So if I want the radians, that'll be the 3/2 pi meters arc length divided by the 6 meter radius. So before I even do any math, we should mention that meters cancels, and radians are unitless. There's no like dimension to them. I guess the unit is a radian, but there's no dimension to them. It's not like meters is one-dimensional, meters squared is two-dimensional, gives you area. These things are not any kind of distance. They have no dimension. So meters is gone. We just have to do this 3/2 pi over 6. That's the same as 3/2 pi times 1/6. I can pull a 3 out of both of those and leave a 2 on the bottom. So that should give me pi over 4. So according to this 45-degree angle is pi over 4 radians because it has a 3/2 pi meter arc length and a 6 meter radius. So let's run through this essentially exact same example one more time with a different radius to make sure that we're still getting the same radians. We'll do this new one in green so it stands out as different. This time let's use, so we did 6 before, let's do 10. 10 seems fine. So if we have a 10 meter radius, that means that our circumference should be 20 pi, because we're just going to multiply this by 2 pi to get the circumference. This is always the circumference of a circle, 2 pi I. So the arc length should be 1/8 of 20 pi meters. Again, 1/8 because 45 degrees we know is 1/8 of a circle. 90 degrees is 1/4 of a circle. This is half of that, so 1/8 of a circle. So this should give us an arc length of 20 pi over 8 meters, which is also known as, you can take a 4 out of each of those and get 5 pi over 2 meters. So 5 pi over 2 meters is our arc length. Let's slide these numbers into the radian formula to figure out how many radians that is. Arc length, 5 pi over 2 meters. Radius is now 10 meters. So again, meters cancels, leaves us with radians as a dimensionless measure. 5 pi over 2 divided by 10 is the same as 5 pi over 2 times 1/10. These guys cancel, leave you with 2 on the bottom. We still get pi over 4. So, you can change this number around to whatever you want. It can be anything. Definitely doesn't matter. As long as this is a 45-degree angle and you're looking at 1/8 of a circle, you will always get a radian measure of pi over 4. So this thing definitely is very sort of robust to changes in size. You change the size of these measurements, as long as the angle stays the same, this radian measure will stay the same, which is what we want as a measure of angles. So let's talk about, that's what radian means, it's how it's defined. And because it is defined like this, that's what makes it better than degrees. The definition of a degree is just 1/360th of a circle, and the reason they chose that number 360 is mostly arbitrary. It made sense 3,000 years ago. It made sense to keep using it 300 years ago, but it doesn't make any sense now. That number could literally be anything, and it wouldn't change anything meaningful about the size of a circle or what a degree is. This is meaningful. This has a definition. There's a reason for its existence like this. That's why it gets used in calculus and a lot of sciences. But still, we need to talk about converting between our units. If we're going to keep using this analogy of metric versus imperial, then we should talk about conversion rates. If you are the kind of person who grew up using imperial units, like inches and feet, when you started learning about metric, one of the first things you learned was how to convert between the two. So they told you that an inch was 2.54 centimeters, and a mile was 1.6 kilometers. These are the conversion rates. So now that we're running radians alongside degrees, we need to talk about the conversion rates. There are two basic ways to do these conversions. The one that I really like is just to use proportionality. For example, we already know that 45 degrees is pi over 4 radians. So if I wanted to know what 90 degrees is, I should be able to just multiply this by 2. 2/4 is 1/2, so that would give me pi over 2. If I wanted to get up to 180 degrees, I could multiply by 2 again and get pi. If I wanted to get down to 60 degrees, I could divide that by 3, that would give me pi over 3. 30 degrees should be half of that, that would be pi over 6. 360 degrees, a full circle should be 2 of these, so that will be 2 pi. 2 pi is a full circle in radians. So this idea of proportionality, that you can, as long as you have one sort of anchor point to use, you can always find out any other point by just examining the proportionality of these things. To figure out what you have to multiply your anchor point by to get 90 or 180. Going from 45 to 60 is kind of difficult, because the number you have to multiply 45 by to get 60 is 4/3, which is not a great number to multiply by. But you don't have to go directly to 60. That's the beauty of proportions. You can go from 45 to 90 to 180 and then divide down to get to 60. Proportions are very nice. If you have numbers that do not line up nicely with proportions, which you'll definitely get some of those, we can use sort of a formula. The formula is based off of this idea. 360 degrees is 2 pi. That's a full circle. So if you have x degrees and you want to turn that into radians, we can first divide by 360 degrees. When you divide however many degrees you have by 360, what you're left with is a percentage. That will get you a percent of the circle. So if you have 90 degrees, you divide by 360, that leaves you with 0.25, means you have 25% of a circle. That percentage has to match your number of radians over 2 pi. So x degrees over a full circle has to always be the same as your number of radians. I'll call it r. R radians over 2 pi. Degrees over a full circle, radians over a full circle, they have to give you the same percent, so they have to be equal to each other. This is sort of the root of the formula. The formulas that they'll present in the book or in the homework are simplified versions of this. So like if you wanted to solve this for radians, you would multiply both sides of the equation by 2 pi. That would give you 2 pi x over 360 equals r, which simplifies into pi x over 180. You cancel the 2 out of the top and bottom. So if you take this x and multiply it by pi over 180, that will give you radians. This is the x degrees, I'll say. This is the formula as it's presented in the book, I think. If you're going in the other direction, you just flip that ratio upside down. Radians times 180 over pi, 180 over pi will give you x degrees. So these are the two ways to move back and forth between radians and degrees, the two unit conversions we're going to work with. Proportionality is the nice one. I like the proportionality. This is a neat trick if you have numbers that are not nicely proportional, like 17 or pi ninths or something. I guess pi ninths is very nicely proportional. If you have pi ninths radians, that's probably just 1/9 of this, 20 degrees. That's not so bad. Proportionality works probably better than you expect it to. There's two more things we need to talk about. I will put those into a third video so that I can cut this one right here and leave it pretty short.